Okay, today we are going to talk about, we're talking about some more series tests for convergence. We've got 2 comparison tests and 1 thing called the ratio test. Coming up on Friday, project number 8 is due. Questions on the calendar? 7. Project 7 is due. Any questions on the calendar?
So we have
okay.
test 3. We have a quiz.
Yeah, we have a quiz that is due on the 27th, which is Monday. So I'll hand that out on Friday.
Oh, okay.
Yeah. Yeah.
So then it's test 3 and then it's final.
And test 3 and then the final. There's a 5th quiz. Yeah, but the final exam is May 20th. It's about a month away. We're getting down to it. Yeah, Ted and I planned it that way. All right, 27. If we could, we would have made it for the same time. Yeah, like left hand calculus, right hand physics. All right, so I mentioned the summary. We're doing comparison tests and something called the ratio test, and then an apology. Today's lesson involves a long demo and a short activity. I am sorry, but I'm giving you fair warning. All right, number 1 talks about reviewing the convergence tests we've already studied by looking at the reference sheet on that separate handout. Do you guys have that handy? Let's just take a quick look at that. It was a separate page. It's not the first page, it was a separate page. It looks like this. It should be on Moodle. It was just a separate document. Okay, so let's take a look. If I've got one, I'll give it to you. Otherwise, you can print it. All right, so let's take a look at this sheet here. Okay. All right. So you will have this sheet with you on the quizzes and the tests and the final, but you got to know how to use it. So let's take a look at the test that we've already seen, make sure we're solid and that we can use this sheet. So geometric series. You use the test when you have a geometric series. So you got to know what that looks like. If you happen to have a geometric series, then you divide the one guy by the previous guy. Here it's called R for common ratio. I think we used a different letter in the notes. X was our geometric series thing. And the series converges if R is between -1 and 1, and it diverges otherwise. The -1 is in the second part. Yeah. Okay. Then, yeah, Laya? You need to get a consistent X from some point forward forever. That is not a geometric series. Geometric series needs to be multiplying the terms by the same number, like the blue. If you look at the bottom row in the blue, what do we multiply by every time? 2, and it's consistently 2. So it's got to be consistently the same number every time to be a geometric series.
Multiplier can't be doing multiply.
Yeah, it's got to be a constant multiplier.
But what if it's an equal amount of proportional amounts of multiplication?
Then it's not a geometric series. It's got to be the same multiplier. All right. In the activity from last class was something called the P-series. Now, I think that most folks didn't get to this, but I had mentioned during class, hey, this is really important and make sure you get to it. So I'm hoping that you had a chance to go back after class and take a look. But a P-series is a series of the form 1 over n to the P. So for example, I don't think I can write on this guy. Nope. So I'll just write on the whiteboard. A couple of P-series. So for example, sum of 1 over n squared and sum of 1 over n to the 5th and sum of 1 over the square root of n are all P-series. They all look like 1 over n to a power. And again, this was important, but it was kind of buried in the activity. So we got to make sure we know what it is. If you see any of these kinds of series, we automatically know whether it converges or diverges based on what you did in the activity. If the P, the power, is greater than 1, the series converges. If it's less than or equal to 1, it diverges. So sum of 1 over n squared, converge or diverge? Converges. 1 over n to the 5th, converges. Because this is to the 1/2, which is smaller than 1, okay? So P-series are really quick, really easy, and they're going to be useful to us today. We had something called the nth term test for divergence. If the terms themselves did not go to the magical number 0, then the series has no chance of converging. Right? Okay, the test tells you nothing, however, if the terms do go to 0. So we've got to make sure we don't read anything into that test that isn't there. Just because terms are going to 0 doesn't mean the series converges. For example, 1 over square root of n, those terms go to 0 if n gets big, but the series itself diverges if you add them up forever. Okay, and then I think the last test we talked about last class was the integral test. So what we needed was a function that was both positive and decreasing the whole time. And then the conclusion was that the series and the integral both do exactly the same thing. They both converge or they both diverge. So if the integral converges, then so does the series. And if the integral diverges, then so does the series. If you can't find the integral, then the integral test is not useful to us. We need to be able to calculate an integral to use it. Any questions? If it's increasing and always negative, then it's just like there's a mirror image thing, but we just say, let's just use that. Questions on how to use this document? Okay, so back on page 27, we'll go to number 2. Can we go to Levi for 2? Okay, so we're going to determine convergence or divergence and write complete sentences as usual. So here's our first one, sum of 1 over 3 to the n plus n. You could write out a few terms if you wanted to get a handle on what was going on here, and you'd see it's definitely not a geometric series. Is it a p-series? 1 over n to a power? Not a p-series. Can we integrate that thing? I can't integrate that thing. Maybe you can, I don't know. So splitting it into 2 seems reasonable. Can we split that fraction into 2 fractions? We can't. No. You can see that's what part B is, and A and B are not equal, right? We can split it into 2 fractions if the top has the plus and the bottom is a single number, but not here. L'Hopital's rule to do what? Yeah, so let's do that. So if n gets really big, what happens to the bottom? Gets big, so the fraction goes to 0. Does that tell us anything? No. So we're hoping for not 0, right? Okay, so we don't have the tools yet, and that's what we're about to develop here. So what we're going to do is compare this guy to a series that I do know what's going on with. So the series I'm going to compare to is well, you could compare to 1 over n. You could also compare to 1 over 3 to the n. You guys agree these are 2 series that are kind of related to the one in question. Let's talk about what each of these 2 series do. Sum of 1 over n, converge or diverge? Sum of 1 over n, that guy's special. It has a name. What's the name of this series? That's the harmonic series. It will appear many times, and the harmonic series flat out diverges. We could also think of it as a p-series. If the power, which is 1 in this case, is anything less than or equal to 1, it diverges. So this guy diverges. Super. 1 over 3 to the n. If you think about listing the first few terms, 1 over 3, 1 over 9, 1 over 27. What kind of a series is that? That's a geometric series. What's the ratio for that series? It is 1/3. So does this series converge or diverge? So this is a convergent geometric series with, I think we're calling it x now, x equal to 1/3. Okay, so we've got our 2 comparison series. Let's see if either of them is helpful to us. I would like to compare just terms now, not the whole series, but just some terms. 1 over 3 to the n plus n to 1 over n. Yeah, in order to compare these, we probably want to just look at the bottoms first. So the first guy, if we just look at the bottoms, the first guy is bigger. So when we flip them, smaller, yes? Okay, so the question is this helpful to us? I have a series that is smaller than something which is divergent. Does that help? No. And you remember, this is what Levi read, is that we had a comparison test for integrals that was the same idea, right? If your integral is smaller than something divergent, we don't get anything out of it. So this is true but not helpful to us, right? So let's look on the other side. Now we're going to compare 1 over 3 to the n plus n to 1 over 3 to the n. That's this guy. And it's smaller, same argument as before. Does this help us? It does, because the series that I want is smaller than something which is convergent. And that's what we need. So I'm going to put some big lines right through this. This was not helpful to us. But we had 1 over 3 to the n plus n smaller than 1 over 3 to the n. And the sum of 1 over 3 to the n does what? Converges. We see that our series, 1 over 3 to the n plus n, what does it do? Also converges. So we're going to have two different comparison tests. So I'm going to call this one DCT for the direct comparison test. And we'll see the other one in a minute. So that's the direct comparison test, where you compare your series directly to another one whose behavior you already know. Okay, if we're good with that one, move on to part B, which is 1 over 3 to the n plus 1 over n. And again, we can do the same kind of thing. We're going to compare to the two individual pieces. So let's see, 1 over 3 to the n plus 1 over n. How does that compare to 1 over 3 to the n? It's bigger, right? Because we added some stuff. It will. And that's why we'll just formalize it here. Is this helpful? Our series is bigger than something which is convergent. Helpful? Not helpful. Let's try the other one. 1 over 3 to the n plus 1 over n. How does that compare to 1 over n? Also larger. So our series is bigger than one which diverges. Helpful or not? It's helpful. That's the useful direction. So what can you say about our series? It also diverges. Again, direct comparison test. We're going to write down a sentence. Go ahead and take a moment. Write down a sentence quite similar to what's up here in black. You can split them up. I wanted to key in on the direct comparison test. Okay, so hopefully we got a sentence similar to this one. Just have to make sure you get all the pieces in there. It doesn't need to be word for word. My favorite word in that sentence is the word also, because that gives me the impression that you really understand this test. It's because the series we're asking about does exactly the same thing as the other series. It also diverges in this case. Okay, let's take a look at the next part, C, or 3. What goes wrong when we try to use the comparison test or the direct comparison test on this series? Okay, so for this one, again, let's ignore everything except what we think is important. If n is really, really huge, then adding this plus 1 at the bottom makes hardly any difference, right? And in fact, adding that plus n at the bottom also hardly makes any difference, agree? The n squared is going to dominate on the bottom. So I'm not putting equals here, but I'm going to say that I'm going to consider that this series is probably quite similar to just ignoring the n plus 1 on the bottom, that series. And this guy simplifies to 1 over 2n. Yep. that series converge or diverge? Diverges because it's the harmonic series, it's half the harmonic series. Yeah, right, you can just pull that 2 right in the front as a half. Okay, so that series, the blue one, definitely diverges. The question is, how does the black series compare to the blue series in terms of like the terms themselves? So n over 2n squared plus n plus 1, and I'm compared to n over 2n squared. What can you say about the first denominator? It's larger. So then when I flip it, it becomes smaller. Sticking the same thing on the top doesn't affect anything. So it's smaller than a divergent series. Helpful? Not helpful. So even if we know in our heart of hearts, the series has to diverge. It has to behave like this n over 2n squared. We can't use the direct comparison test. The direct comparison test is really limited in value because things have to work out just so in order for it to work. So on the next page, all our troubles go away. And so instead, we're going to do something called the limit comparison test. And you can see that I'm comparing to just 1 over n. I didn't put the 2 in there. You can include it if you wish. You don't need to. So here's the limit comparison test. What we're going to do is find a limit as n goes to infinity. So this is a brand new test. Limit as n goes to infinity of the term in the series that we're interested in, n over 2n squared plus n plus 1, divided by the term in the series that we think ours behaves like, 1 over n. Everybody see the two things? The original term, and then the one that we hope we can compare to. Okay, so it's kind of messy with the fractions within a fraction. So how about we flip that bottom 1 over n upstairs? So what does it become? N squared up on top. I'm hoping we can just figure out what that limit is just by looking at it. It's a half. Yep. Because we can ignore everything except the leading terms, right? So upstairs is n squared, downstairs, all that we care about is 2n squared. So this limit is a half. We don't need any justification. Sam had mentioned L'Hopital's rule. If you really want to justify, you can use L'Hopital's rule a couple of times. You'll get a half. Okay, so here's the conclusion. As long as that number that we just got there, that 1/2, as long as it is not 0 and not infinity, it's pretty strange conditions, not 0 and not infinity, then the two series behave the same way. That's the conclusion. This is written up in the next problem. But I'll say it again. As long as that limit is not 0 and not infinity, then the two series behave the same way. Yeah, I mean, finding limits is supposed to be a lot easier than finding what's happening with series. So hopefully we have limits that we can handle. Yeah, n cubed on the bottom would be 0. Right. Okay, so here's our conclusion. I'm going to give this guy a name right here. I'm going to call it L just so I can refer to it. Since L equals 1/2 is not 0 and not infinity, not 0, not infinity, strange conditions. The two series behave the same. What about graphs? If you could integrate the original, then you wouldn't need to do any comparing. But doing integrals is pretty hard. Oh, as integrals. Yes, absolutely. Yeah, gotcha. Okay, LCT is the limit comparison test because fundamentally we're doing a limit here. Okay. All right, so we got to finish. We're not quite done. What did we say about the purple series here? diverges. That's the harmonic. So what about our series? Also diverges. So then we'll just say, since sum over n, 1 over n is the divergent harmonic, then our series, and I'm just going to write it, also diverges. Yeah, way more powerful than the direct comparison test. Doesn't even need to be less, just needs to be not 0 and not infinity when we do this limit. You do, but we're going to choose wisely. I mean, we're only going to pick things that we know about already, like 1 over n, and all the p series on the board are now easy. Geometric series are easy, so we're going to pick easy things to compare to. Okay, so let's talk about, all right, so here's the details of the limit comparison test. So you start with all non-negative terms, and as long as this limit is finite and not 0, then they either both converge or both diverge. Notice that it makes no difference which one you put on top. If we had put, I put the original series on top and then the comparison series on the bottom. But if you flip it over, what's the limit at the end? 2, which is also not 0 and not infinity. So it makes no difference. You don't have to remember, oh, which one goes on top. Okay, so let's look at the strange comparisons, the finite and not 0. Let's take a look at this pair of series right here. Sum of 1 over 5n and sum of 1 over n squared. Is there any reason to believe that they behave the same in terms of they both converge or they both diverge? No, they're not the same, right? One of them is an n and the other one is an n squared. They are fundamentally different things. Let's see what the limit comparison test would tell us if we decided for some foolish reason to try comparing these two series that are apples and oranges. So 1 over 5n divided by what? 1 over n squared, right? This is the limit that we would find. N goes to infinity. What is this limit equal to? N over 5, which becomes infinity. So does the limit comparison test apply? No, because we were foolish. We decided to try comparing two things that aren't comparable. You got to match the powers, right? I mean, that's how we came up with 1 over n on the previous examples. We matched the powers. What if we had done this in the upside down order? Limit as n goes to infinity of flipping this whole thing over. I'll put the 5n over n squared, right? If we just flipped it over from the beginning. And what is that limit? 0. Does the limit comparison test tell us anything? Well, yeah, it tells us we were stupid for trying to compare two things that aren't comparable, right? So that's the 0 and the infinity. Is the limit comparison test saying, hey, dummy, these don't necessarily behave the same way. Pick more intelligently, okay? So maybe not so funny looking, the 0 and the infinity. The limit of those terms is approaching infinity, meaning the 1 over 5n is way bigger than the 1 over n squared. This is the ratio of terms from two different series. So those aren't terms from one series. Okay, so number 7 says, what's the problem with the limit comparison test for this guy? It says, let's try it. Okay, so what might we try comparing this thing to? Let's pick it apart. One option. I want to make it simpler. So this is a reasonable thing to make it simpler, right? What's the other reasonable thing to make it simpler? Just n squared. Let's just break it down into smaller parts and see if anything is useful, right? Okay, so yeah, so let's compare these guys. So if I were to look at the original guy and divide it by my first option here, this 1 over 2 to the n. What happens to clean this up? So it's just n squared, right? Right, these 2 to the n's cancel. And when n gets big, so does that. So we can't compare it to 1 over 2 to the n. They're not similar enough. And if instead we had decided to take ours and compare it to the other guy, n squared, the n squareds cancel in this case. And that goes to 0, which again, we're out of luck. It is, but and I'm not saying that that series behaves differently than 1 over 2 to the n. 1 over 2 to the n converges. I'm just saying limit comparison test is not the tool. But I mean, I think Elia is saying that this n squared is, you know, kind of moot, right? I mean, like compared to the 2 to the n squared is just dominated, right? So it feels like it's just going to be like 1 over 2 to the n. All I'm saying is that we can't use this tool. Yeah, and it's bigger than something that converges, so we just can't use it. Never fear. Ratio test is here. Okay, so here's our third and final test for today. We looked at the comparison test where we directly compare. Then we looked at the limit comparison test. And now finally the ratio test. So it says if you have a series and you decide to do the next term over the current term, which by the way, that fraction we have seen before. We saw it on the reference sheet today. That's the geometric series fraction, right? Because you take the next guy and divide it by the current guy and you hope it's always consistent. Well, okay, maybe we don't necessarily have a geometric series like a full-fledged geometric series, but maybe it's really close to being geometric and it approaches some limit L. So what were the good ratios so that the geometric series converges? -1 to 1, smaller than 1, basically, if everything is positive. Less than 1 was the convergent part. Well, look, if L is less than 1, then the series converges. That's the conclusion of this ratio test. If L was bigger than 1, if the ratio was bigger than 1, the series diverged. Still, if L is bigger than 1 here, the series diverges. Sadly, there's a third condition, which will be the unhappiest condition that you'll see. If you happen to get a limit equal to 1, the test is inconclusive. The series could converge or diverge. This test just doesn't help us. But let's see where the test does help us. How about this example part A, which we couldn't do a minute ago with the limit comparison test. So here's the idea. I'm going to call L. The limit as n goes to infinity. Okay, this one, the order does matter. You have to put the n+1 version on top and the n1 on the bottom. So the n1 on the bottom is easy because it's just copying whatever the original rule was. So down here it goes n squared over 2 to the n. Upstairs, it's easy once you know how to do it. All we do is change all the n's to n+1s. That's it. All the n's become n+1s. So n+1, n becomes n+1, and it's squared. N becomes n+1. You could FOIL the top. Yeah, I mean, you could. I don't know that we need to, but you could. Any questions on setting this thing up? According to the ratio test, I am missing something. What did I omit? Absolute value. So let's put them in. In this case, everything is positive, so it doesn't matter, but we'll put it in anyway. Okay, equals limit n goes to infinity. So now I'm not going to write the absolute value because everything is positive. And I'm going to flip this guy from the bottom upstairs to the top. So I have n+1 squared. And then who else is going up there? 2 to the n. And then downstairs I had this 2 to the n+1. And now who else? N squared. Everybody see that? flip the bottom guy up to the top. Okay, so good things are about to happen. Let's see. I've got 2 to the n and 2 to the n plus 1. Lots of stuff cancels. What's left? 2 on the bottom. Yeah? Because you have one more 2 downstairs than you do upstairs. So since there's just a 2 on the bottom and there's no n's anymore on that thing, I'm going to pull it out front in front of the limit as a 2 on the bottom. And then I'll copy what's left. Because downstairs you have a single extra 2 more than you had upstairs. Because it's 2 to the n plus 1, so you have n plus 1 of these 2's sitting down there. You can do that. It's this property. Yeah. Okay. What is this limit? Is it infinity? 1. Yeah, it's the leading terms. So Alex had said, you know, can we FOIL? You can. I don't want to. But let's just imagine if you did FOIL, what would you have on the top? N squared plus some stuff that we don't care about, right? So n squared is the dominant thing on top. Downstairs is just n squared. So that limit is plain old 1. It is n squared plus 2n plus 1. But yes, the 2n goes to infinity, but it is dwarfed by the n squared, which is going to infinity so much faster. It doesn't, before we think about canceling the n squared on the bottom, we got to think about what's really happening on top. And really on top, the n squared is the only part that matters. If you plug in a billion for n, a billion squared is so much more than the 2 times a billion that you were talking about from the foiling, right? N squared is so much bigger than 2n. Yeah, so you cannot just cancel the n squared and look at what's left, because as Rob says, there's additions on top, right? You could. All right, maybe we like that. So we break it apart. You don't need to write this, but if you want to see the details here, and this is an important piece, so I don't mind spending a moment on it. But I need us to get to the place where we can just say, oh yeah, that limit is 1. So if you want justification, what about this first fraction? That's 1, definitely. As n goes to infinity, what about the second fraction? Goes to 0, right? Because the bottom is so much bigger than the top. That's why it's okay to ignore the 2n, because it's getting compared to the n squared that's just hanging out in the bottom. And then 1 over n squared, really 0, right? Okay, so this limit turns out to be a half. All we have to do is go back up to the ratio test and decide, okay, what does that tell us?
Converges.
Converges because that 1/2 is less than 1, that's all. So we'll write our, what it tells you is that the series that we started with is basically a geometric series where the ratio is a half. If you go out to a million and beyond, pretty much the next term is half the previous term. It's not perfect because that n squared kind of throws a wrench in. It's not exact, but it's honing in on a half. Yeah. Okay, so since L equals a half, which is less than the magical number, which is 1 in this case, let's copy the original series, n squared over 2 to the n. What does it do? Converges by the ratio test. Not everything. We'll show you an example in a moment where it doesn't work. We'll get to a conclusion where I'll give you some hints as to when it's good to use this one and when it's not so great. No, these are specifically series results. No, as long as the function that you're integrating is decreasing and positive, then the integral test says that the integral and the series behave the same. So they have the same behavior. So this integral, like if you did this integral, n squared over 2 to the n from 1 to infinity, you would get a finite thing because this guy converges. They just have to do the same thing. Yeah. Okay, moving on to part B. First appearance in a long while of what symbol? Factorial. You guys remember the gamma project, right? This will not be the last appearance of factorials in our class. So it's in the ratio test section. Let's just jump in with the ratio test and see what happens. So L equals limit as n goes to infinity. Big old fraction. You guys are going to get really good at your fraction canceling properties. I always start downstairs. That's easy. What do I do downstairs? 4n over n factorial. Just copied, right? The term itself always goes downstairs. So I begin there. And then upstairs, all the n's become n plus 1. So I go 4 to the n plus 1 over n plus 1 factorial. Again, what am I missing? Absolute value, we'll just throw it around everything and then not write it anymore because everything's positive. It's a good question. 4 to the n is what kind of a function? Exponential. And you've been taught that exponential dominates everything, right? Like exponential beats everything. Okay, so yeah, like n factorial wasn't in our list of things we were comparing to, so we didn't have reason to talk about it. But suppose that we look at, for example, 4 to the 10 compared to 10 factorial. So this is 4, 4, 4, 4, right? 10 of them. And this is 10, 9, 8, 7. Who wins? Doesn't that, I mean, do you have 10 numbers you're multiplying? In the factorial one, most of them are bigger than 4. So who wins? Factorial. And so when we said exponential beats everything, we didn't let factorial into the party, which is a good thing because factorial would dwarf exponential. Look, and we're only at 10. Imagine you were at 100. So you could have 100 copies of the number 4 all multiplied, or you could have 100 other numbers, 100 times 99 times 98 times 97, right? I know. You guys appreciate factorials now. What if it were 10? What if it wasn't 4 but something bigger? Yeah, so what if that 4 was a 10? Yeah, the exponential might hold its own ground a tiny bit longer. But the factorial one has to win because every time you plug in a bigger number for n, the bottom gets multiplied by the next number up, whereas the top just keeps multiplying by 4 or multiplying by 10 or whatever. Every time. Okay, so let's do our common trick of flipping the thing on the bottom. Okay, so who else goes upstairs now? N factorial, and then downstairs 4 to the n. Yeah, so we're starting to see some common techniques here, right? Those 4s mostly cancel. How many are left and where? 1 on the top. So I'm going to write the 4 in the front. And then we've got this factorial business, n factorial over n plus 1 factorial. Okay, now we have potentially no experience manipulating factorials. Like, you know what 10 factorial means, but can you simplify n factorial over n plus 1 factorial? For most of us, it's probably a no. You never thought about doing this. Before we simplify it, do you have a guess? What is this limit? It will be. But guess for the limit? The top is n factorial. The bottom is 1 more factorial. It seems like, to me, it feels like it shouldn't make a difference. It feels like it's a 1. It feels like that limit is a 1. In the same way that this blue thing up here, in the same way that this was basically top and bottom basically the same, so it's a 1. So it feels to me like it's a 1 down on the factorials, but I'm wrong. It isn't a 1 on the factorials. But the bottom is only 1 bigger, so what difference does it make?
Depending on what it is, go for 9 factorial.
Yeah, so 9 factorial on top over 10 factorial on the bottom. What happens when you cancel? Sam says 1 over 10. I think Brendan agreed. This is true? Is it right? Think about what 9 factorial means. 9, 8, 7, 6, 5, 4, 3, 2, 1. 10 factorial. 10, and then exactly the same stuff we just said. So all of the stuff from 9 down cancels. So it seems like, I mean, there's plenty of things that like you want to do, but canceling factorials is not allowed because that limit is now 1. Yeah. So this guy in reality is 1 over n plus 1. We buy it? There's one guy left downstairs on the bottom. It's n plus 1. Everything else cancels. And this limit is 0. Yeah, the bottom dominates the top. Okay, so go ahead and write a sentence. Should be quite similar to the sentence. I'll flash it up on the screen again. Quite similar to that sentence in black. What was the limit in this case? 0. And 0 is less than 1. Same conclusion for the same reason as the previous one. Okay, so I didn't write the sentence, but I'll just say it. Since L equals 0, less than 1, the series, and then make sure you copy the series, 4 to the n over n factorial, converges by the ratio test. Questions on that one? Could be. All right, let's try part C. Part C is one that we've done already today. You guys remember we used the limit comparison test on this one. And Elia had suggested, well, hey, the ratio test seems like this almighty and powerful thing. Can we just use it everywhere and get rid of some of those other tests? So let's try it on this. Okay, so we begin with our standard limit calculation. Beginning on the bottom, what do we put? The same thing. Upstairs, all the n's become n plus 1, so be really careful. Pretty much all the n's should get parentheses around them and become n plus 1s. Okay, I'm going to be a little bit lazy because there's just a lot of writing here, so I'm just going to cross this off and flip it upstairs. So what goes on top? And downstairs. N? Everybody okay with that? Just flip the bottom guy up. Okay, so now we're really going to wave our hands here to calculate this limit. In order to figure out what the limit is, all I care about is leading term on top and leading term on the bottom. So I'm going to imagine doing a lot of distributing, but very greedily just looking for the leading term and not doing anything else. So what is the highest power if you distribute this n plus 1 times this 2n squared plus n plus 1? Is n cubed, yep? 2n cubed is what's on top, plus a lot of stuff we don't care about. So I'm going to write this over here. Equals limit as n goes to infinity. It's 2n cubed plus stuff that we don't care about. Downstairs, a lot of distributing to do. First, you would need to FOIL the n plus 1 squared and distribute, or and maybe combine some terms, and then multiply everything by n. But all we care about is the leading term. What is it? It's 2n cubed. And then some stuff that we don't care about. So this limit is 1. So what does the ratio test tell you? The test is inconclusive. We did. So the other test, we already saw that series diverged. But I just want to, this answers Elias' question. The ratio test is not this like cure-all. It doesn't always help. Okay, on the next page, I think, is our conclusions. Who are our readers? Cameron, can you read number 10? Okay, so this is supposed to help us. If you see a factorial, you're definitely using the ratio test. But if you see polynomial over polynomial, don't bother with the ratio test. Okay, and then 12. Eli, have you read already? Did you? You did. Gabe? There's no 11. Caitlin strikes again. I'm pretty sure I wrote this. Gabe, number 12. Yeah. Gabe, number 12, please. Okay, so the activity is on the next page, and I want to make sure that you know that these are now all kind of mixed together. It is not just today's tests on the activities, all right? So make sure you go back and look at all the different tests you have and carefully and slowly work your way through. Raise a flag if I can help.